So abstract algebra, when we have words like groups, rings, fields, etc., and I'm going to show you the others, works this way. You have a set to which some specific axioms apply, and then if you add or remove axioms, you then get another set. So for example, we have something called the abelian group. Abelian group. Abelian group, does anyone know the synonym for the abelian group? A problem with these synonyms, I mean, exactly, a commutative group. Commutative. And why is it called commutative? Because you have axioms 1 to 4 plus a fifth axiom, which is commutative. Simply means if you multiply A times B, it's the same thing as multiplying B times A. Now, of course, you will come across certain sets in linear algebra where this is not the case. Because, for example, if you want to multiply a row by a matrix, what am I saying? A vector multiplied by a matrix, you cannot turn them around. So what is it if you want to multiply a vector with a matrix, the number of columns must match the number of rows. So you can't just commute them around. It's not the same thing, okay? But anyway, this is not specific to vectors and matrices. It's just, it can apply to different types of sets, different types of mathematical objects. And then we have a ring. Maybe just copy paste the whole set of axioms. You'll see where I'm going with this very shortly. We have the ring. A set to which the following axioms apply. You have associativity for addition, commutativity for addition. There is this zero element. So there's an element, this is incorrect, by the way. A plus 0 is A. A plus 0 is A. Okay. There is additive inverse. So similar to what we saw with the group, there's an element, the inverse of which will give you, that one gave us identity, this one gives us 0. They cancel, for here in addition, they cancel each other out. We of course have associativity, this is for multiplication. So associativity and commutativity for addition, and the same for multiplication. And then there's unity, like with groups, and then there is the distributive law. Then there is a special type of ring called the integral domain. And this is a set, this is a type of ring, it is a set, of course, with axioms 1 to 8, but not 7. So unity does not apply to an integral domain. Then there is the field. This is the word we encountered when we were talking about linear algebra. So linear algebra is a type of ring with axioms 1 to 8. So it has all 8 axioms plus a 9th axiom, the multiplicative inverse. That's what a field is. Now, I really don't know where these names came from. Ring, I remember seeing a very fascinating page, and there was an illustration about it forming a ring. I don't remember, unfortunately. But the names, in my opinion, they're not very intuitive. Like, why field? You know, they're not helpful, but that's how it is. Now, so I hope it's clear what a field is, right? A field is a set with, or I should say, to which these rules apply. Axioms are rules. So this is an axiom means something that is true for all the elements of that set. Okay, so to all of the elements in a ring, you can apply these rules. This is true. Why are these even helpful? Because these axioms will give you confidence that whenever you apply such operations to any element of the set, you can be sure it will hold. If you're doing things like proofs, or if you're formulating a model, axioms will really help you get to a solution faster. Anyway, so a field is basically a ring, but we also have a 9th axiom, the multiplicative inverse. So we will see examples of vectors. When you multiply it by its inverse, you will get the original vector. This is not something you can do to objects in the let's say integer number system. Okay. So let's return back to this linear algebra tutorial. Scalar multiplication. And this has to be, I will use C to stand for component. Yeah, so hopefully you can see that this is a ball, so that's a vector, that's a constant. Multiply the scalar by the vector, you will get another vector. You will get a vector that obviously that will be a subset of the vector space. Okay. And V is a vector. I will say here that this is a subset of the real number system. And this is a constant component. Let me now show you a linear combination. What is linear combination? Linear combination. And let me talk about R to the power n. What does this mean? Let's say to the power 3. What does this mean? So basically, you will get a set. Let's use the word space to be consistent with linear algebra terminology, with any 3 letters, elements or components, any points, all of which belong inside the real number system, such that A, B, C, all of them are in R, or the real number system. Okay, so for example, this could be a point in a 3-dimensional space, or it could just be a vector. It doesn't necessarily have to be a point on a coordinate space. It just could be a set with 3 elements in it. So that's what this means. So for example, R to the power 5, same thing. A, B, C, D. This should be R. Okay, so here it says so now that we know what that is, the linear combination. A linear combination is, let's say we have vectors, and here I'm using the bold arrows. From V1 to VK. By the way, when I see N or K or some subscript like that, I either pick the number 3 or the number 5. Helps me visualize things. So let's say we have 5 vectors. This is a vector 1, 2, 3, 4, 5. All of them are, for example, in 3 dimensions. And associated with each vector is a constant, which are real numbers. So you can see there's no superscript here because these are scalars. So what's an example of a linear combination? Something that looks like this. Evaluate this expression, and you have your linear combination. Now, what's a linear span? A linear span is the following. Say we have a vector space, basically a set of vectors, a set containing vectors. And we have, let's say, 5 vectors. So we have a space, a vector space V, with elements V1, V2, all the way to VK. And then we put these vectors inside a set called X. Okay, so we take these sequence of values, so they're all vectors, we put them inside the set X. If we apply this linear span function to X, then we will get the following. we will get a set of linear combinations. So that's what a linear span is. A linear span is a set of linear combinations. If you remember from, we talked about self-product notation, we said that this is, well, this is a set with these elements such that the V's are vectors and these are the constants. So a linear span is a set of linear combinations. So it's basically a set of these. That's what a linear span is. Okay.